Right. Welcome everyone to day 3 of MuniHac 2022. We hope that you enjoyed the day so far. We hope that you enjoyed the breakfast. And now, coming to our third keynote for this year, we have Nick Wu. Nick is a professor at Imperial College in London. And Nick has a somewhat unusual career. Unlike most, he didn't go from academia into the industry. He went into the industry, worked at WellType, and then went back to academia. He's been researching algebraic effects and recursion schemes. And I think I've heard numerous talks from you at different Haskell exchanges about the various new developments in algebraic effects. This talk, I think, is rather about the basics, an introduction to algebraic effects. And yeah, so we hope that it's accessible to everyone. And thank you, Nick. Give an applause.
Okay, thanks, Hans, for the introduction. All right, so yeah, so this talk is structured in several parts. And I'm dealing with the idea of modular programming with effects generally. So in the first part of this talk, we're going to start thinking about monads and transformers. And then we're going to move on to what are known as free monads, which is basically starting to think about things called algebraic handlers. And then we're going to think a bit more carefully about what algebraicity means from a more theoretical perspective. And then we're going to finish up with something called scoped handlers, which is something that's not algebraic and is an extension of what these things are. But we'll get there when we get there. So let's start with monads and transformers. I've noticed that a number of people here are beginners, and so I thought it would be good to just start with some of the basics to see where we go. So let's talk about expressions. So here is a simple expression language. You've got expressions. They're either a number, which is a double, or you've got an addition of two expressions. And the idea is that we want to actually evaluate such an expression, so we're going to define this eval function over here. And what eval does is if you've got some number x, then you return x. Otherwise, you evaluate the program containing x plus the evaluation of the program containing y. So this thing will eventually just calculate the value of these two things added together. Okay, so we might want to add, say, multiplication to this, and so it's quite easy. We can just extend our data type to have one more constructor for multiplication, and then we can extend our evaluation function so that it does multiplication. So this is all fine. But let's suppose that we did some division instead, and we wrote something like this. Then it's actually quite a dangerous operation. So when we start doing px divided by py, or the evaluation of px divided by the evaluation of py, we might get into trouble because of good old division by 0. So that means that this particular piece of code is no good. We don't really want to ship something like this. So how do we deal with this? And so one of the first things that you learn as a sort of beginning programmer in Haskell is to deal with these kinds of issues is you use a maybe monad that allows you to either return just the value if things have happened successfully or nothing if things have broken. And so that's the idea of what you can do with this maybe division version of the expression handler. And the history of this goes back to originally by someone called Moji, who looked at some category theory and saw how models of effects in category theory worked out nicely using these things called monads. But independently, there was work by Mike Spivey at the end of the 80s, early 90s, on a functional theory of exceptions, where he introduced the term maybe and nothing and just that we use today. And then very shortly after, Phil Modular popularized this for lots of different monads as well. And so if we look at what happens in our evaluation function over here, then the evaluation says that if we have just an ordinary number, then we return just x. So everything is fine. Otherwise, if we're adding things together, we have this annoying cascade of things that we need to do. We check to see the case of the eval. If we get nothing, that means that something went wrong downstream on the left-hand side on the px, and then we return nothing. Otherwise, we got an x back, which is good, and then we can do maybe the evaluation of the right-hand side, py. If nothing came back, then something went wrong on the right-hand side, so we should return nothing. Otherwise, we really got a y, and at this point, we got just an x, and then we got just a y, which means we're safe to add. So we can just do something like this, okay? And in the other case where there's division, well, you evaluate the left part, and then if you get just x, then you evaluate the right part. If nothing happens, something broke. Otherwise, if you got a 0, then this is exactly the case that we want to catch, and so you return nothing. And so this is the thing that propagates the nothings through the system, and eventually your failures will return in nothing, and hopefully you should be happy with that, okay? So um, uh, now let's think about um, uh, what we might, or what we've just done to our addition. So what we've just done to our addition is somewhat mangled it. We started off with a sort of a clean evaluation thing like this, and then we ended up generalizing away to some kind of context that looks like this. So if we go back to the previous slide, you can see that I've got this kind of, this big ball of mess over here. And what we can abstract that to is, rather than being specific to the maybe monad, we can say, actually, we want to do some kind of sequential computation that might fail, and that's going to be happening within some context M, which is monadic, which basically says there's a sequence of operations that we need to interpret before we can proceed. And so we need to tell the evaluator, how do we proceed through evaluating addition? And so what we say is, okay, well, you've got two programs, px and py. First evaluate px, then get the result and call it x. Then evaluate py, get the result and call it y, and then return x plus y. And so this is the sort of the generic scheme that allows you to do addition regardless of the underlying effect, whether that be error throwing, which is what we just saw now, or something else. And so what we can do now is, rather than depending on the specifics of the maybe monad, so I had just 2 slides ago, all these justs and nothings getting in the way, you can instead say, actually, I'm interested in a class of monads M where failure might happen. So where there's this additional operation called fail that, given a string, will fail. Now, as it happens in the maybe monad, that string is going to get discarded, but never mind that, that's just a detail. What we can do now is we can write our eval using this monad fail M constraint, which indicates that we're in some monadic context M, where we've decided how to schedule our computations with evaluation, and where furthermore, things may fail. So this is what this part of the signature does. And so we go through again, and we see, we should see in this code over here that we now make no more reference to the maybe monad. So that, in some sense, was a mistake. It was too concrete. And what we're trying to do here is we're trying to loosen ourselves from thinking about maybe monads specifically and just think about the fact that things may just break. So this is probably the better way to design this program. And so if you have some number x, you return x. Otherwise, well, this is exactly the sequentialization that we saw of add earlier on. And then in this case, for the division, we're going to basically check to see if y is 0, and that's when we omit our failure. Otherwise, we can return the division. So this is a cleaner design, because what we've thought about is what kind of effects could our program raise? Well, failure is an effect that it could raise. We abstract away from that, that idea, and then we incorporate that into our code in this way. So that seems like a lot of work. Why are we doing it? Well, it turns out that, oh, sorry, and there's one more point, which is, well, actually, this is the point. So that was a lot of work. Why do we do that? Because it allows us to instantiate the monad to be different kinds of monads depending on the circumstance that we're after. So here we've got 2 different examples, example 1 and 2. And example 1 is exactly the maybe evaluation that we had earlier on. And this is the same eval that we had on the previous slide, which just worked with a constraint saying that this monad could fail. And now, because at the point of application, when we're trying to actually use this evaluation function, we can instantiate that M to maybe, which means that when this thing is executed, you get nothing because we have a div by 0 going on. But with that very same program, we can give it a different type annotation, this time with either string as our data type, our underlying monad. And then when this example runs, it actually returns the error that we get. So we've afforded ourselves some flexibility in the semantics when we actually do things in this style. So if you're a beginner in Haskell, something that I would urge you to do when you're working with monads is try not to work to a particular monad, but rather work to a class interface for the effects that you're after. Use class constraints carefully to define exactly what you're after, and then when you need to actually use the monad, that's when you can instantiate your types. And you'll find that your programs become much more compositional in this way. So here's a slightly different example. It's the example of square rooting. So we're going to add square rooting to our language. So this is the square root function. It takes just one expression as its argument. And all of the code and top part is exactly the same as before. All we've changed is that rather than having just a monad fail constraint, we also have a monad plus constraint. Now, this monad plus tells you that you have 2 computations. In some sense, you want to accumulate their possible values. And so the mental model that you would have in here is that this is like a list of results that are coming back. So it may be more than one thing that comes back from this monad. So This part of the code remains exactly the same because the monad fail constraint is still in play, so there's nothing has been removed. And what we have now is we're able to say the square root of some program x is first you evaluate the x, and then you return the square root, the positive part, and then you also return the negative part of the root because that's the bit we always forget about. So this is a program that remembers that you wanted a positive and a negative root in your answer. And so having done things this way, as I said just a second ago, we can evaluate our program with different data types to see what happens. So if we evaluate the maybe double, what we get is this OR part, which gives you both the roots, will default to the left-hand side one, and then that will simply eventually give you the 5 that you want. Otherwise, if you want a list of values, then it will give you back both answers to the equation. And of course, if you had several other square roots inside the expression that you were dealing with, then you would have multiple results depending on what you actually asked for. And finally, if you work in the IO monad, for instance, it too supports a monad plus and monad fail, and it just discards the answer, and it doesn't even tell you that it was in the maybe context. It just will return 5 in that context. So, so we have all these different possibilities. So I'm hoping to show you here that there's flexibility here, and there's compositionality going on here, and that's quite a useful thing when we're designing things. Okay, so the thing is, we kind of got lucky, actually. So in the previous program, we were able to write something where the list monad, the maybe monad, and the IO monad just worked, and it was all great. But that's not always going to be the case for all of the effects that you see in play. So here is a different example, and this time I'm saying, okay, we want to get some value y from the state. Maybe we would have done something like increment the y as well and put something back. It doesn't really matter, but the point I'm trying to make here is that we're working inside some additional effect system where we've got some get operations in play as well. And maybe things fail too, so we've got monad state and monad fail. Now, the M that we have here, it neither instantiates to the state monad, nor does it instantiate to the maybe monad. And so the question is, what on earth are we going to do with this program? How do we execute this? So here are some different attempts that you might hack away at to see whether you can get this thing to work. So I want maybe in state, so maybe I have this kind of maybe thing and a stateful thing, or maybe it's a stateful thing, and then you take in some state S, and then you return that S and maybe the answer. Or maybe there's this S here, and then maybe you return the S and the answer. And which one's right? Okay, so you have to kind of figure this out. And in some sense, that's the burden of proof that's difficult when you're working with these things, is you need to work out, well, what are the monads that I want to be using with? So somebody had to work out that there was a way of combining these things, and there was a right way, and there was a wrong way, and maybe there was more than one right way, and there was certainly more than one wrong way, okay? So, so what do we do with this? And in fact, the situation isn't just to do with how state and maybe work out together, it's to do with a whole variety of classes of effects. So here we have monad fail, monad state, monad reader, monad writer, monad plus, monad random. And each of them provides different operations that you can use in your sequential program. So whether that be getting and putting from a particular state, perhaps you're asking for some configuration from a configuration file that you can then depend on later on. Maybe you're telling something to a log file so that you can see where you are inside your execution. Or maybe you're doing this non-deterministic monad plus thing, or maybe you're just getting random values. But the whole point I'm making is that we have to try and find the monad that fits whatever catalog of effects you're interested in using. And then maybe even you're creating your own constraints, your own things. So for instance, if you're trying to do code generation, maybe you emit some instructions and you don't know where they go. They just get emitted and then dealt with in the code generator. And maybe you need some notion of labels, so you can pull off some labels for your go-to statements. And so then the question is, which monad is going to satisfy these things? So you need to design things around this somehow. So there is a burden of proof when you start writing an instance for these monads, and you need to decide exactly how to satisfy that. And so here is a version of the monad class, which says that there are 2 operations that you need to satisfy. And if you give definitions for these, or morally things like these, then you will eventually have a monad class that desugars to the do notation that we've been using so far. So far we haven't seen these arrows at all. All we've been using is do. And basically that's because do notation desugars into these kinds of instructions. And so these are the things that are sort of the underlying primitives. I'm slightly lying to you, actually, because traditionally Haskell uses this bind operation, but it's equivalent to this, what we call Kleisli arrow instead. And the only reason I want to display this is just to make you aware that there are various laws that you need to satisfy when you have an instance for a monad. Otherwise, the monad doesn't behave properly, so sequentiality will give you some strange surprises. And the laws that you want to satisfy are essentially saying something like, if you return, so if you first return and then do something, then that's just the same as doing the thing, so you need to return. If you do something and then return, then that's just the same as doing that thing. And then you have, I guess, what's at the heart of being monadic, which is this associativity law that says it doesn't matter whether you did F and then G followed by H, or F then G followed by H. So these things should be equal. And so it's your burden as a programmer to make sure that your monad laws hold for whatever instances that you decide to put in. So obviously it's easy enough when you're relying on well-known effects, but when you're kind of picking and choosing, and when you're making your own monadic interface and you're thinking how to do things, maybe you'll encounter situations where you need to actually do these proofs. And that's the frustration. Oh, that's strange. Okay. So I was here. Okay. So so now I want to talk about monad transformers, because you don't have to roll your own monad every single time, and you don't have to guess which of those maybe state things you have to play with, because thankfully people have worked hard to do that for you. So there's this paper by Liang, Hudak, and Jones in '95, where they introduced this idea of monad transformers. And the idea with monad transformers is really that you have a way of building monads from other smaller constituent parts. So there's what we call a monad transformer for state, which provides just state, and then that transforms some monad underneath it to have stateful effects. There's a monad transformer for maybe called maybe_t that takes an underlying monad and then gives you the option to fail inside that context. And so you can combine these two things. So you can write things like state TS, maybe TIDA, to give you a notion of local exceptions, or you can have global exceptions by putting them maybe on the outside. So actually there was more than one way of composing things previously, and you can write these different data types as the monad you want to interpret into, and you'll get different semantics depending on which way around you compose things. And thankfully, the proof in this paper shows you that, or proves to us that these things that we've just produced with these transformers, they're well-founded, and everything is good, and we don't have to worry, so we don't have to do any extra work. And before we go into algebraic effects, I want to just note that that's no trivial thing. So if you think about how you would do, for instance, so in the division example, we had lists as the underlying monad that we were trying to work with. Well, what does the list monad transformer look like? And the naive thing that you might do, which is something like return an M around the list of A's, turns out to not quite do what you think it does, nor does having a list of M of A's do quite what you think it does. So the underlying monad needs to be so-called commutative in order for things to work, and if it's not, then you're going to get surprising results. So there's a kind of naive way of doing it, and then that turns out not to satisfy the monad laws, and then there's a more complex way of doing it, and that's, again, the subject of yet another paper. So this is no trivial business. So algebraic effects enter the scene. So these are ideas that came, or at least have become popular more recently. And I would say that the idea behind algebraic effects is that we want to have a syntax tree, and we're going to interpret that syntax tree bit by bit and emit effects as we go. And the great thing about algebraic effects is that the way they're set up is such that proving those monad laws happens automatically. It's built into the framework. So you don't have that burden of trying to decide how to make this thing work for yourself. That's just something that you get for free. So let's have a look at what the free monad is. So the free monad is, here I'm calling it free, and it consists of two parameters. There's a sig parameter, which is the signature of the tree's nodes that we're going to deal with. So the idea with the free monad is it's sort of an abstraction for syntax trees. And these syntax trees are parameterized by whatever signature you want to pass in, so what the operations actually look like. And it also has variables at the leaves of this tree. So you've got this var constructor here, which is for the variables at the leaves. Otherwise, you have some operation, which means you have a syntax node somewhere in the middle, and it's shaped by the signature functor, which tells you exactly what the shape of this node is. And then it continues with more of the tree underneath that particular signature functor. So earlier on, we had this expression language where we had numbers and this addition thing. And what we can do is we can define a functor now. So the k parameter is where the continuation goes. It's where the rest of the program is going to belong for this particular signature. And so we have this numf constructor, which, oh, this should be double double, which tells you where you've got your payload. And otherwise, you've got this addfkk, which tells you that you've got a continuation in both of the two parameters. And the idea is that the expression type is roughly the same as, or is in fact the same as free extra f void, where void says that there are no leaves in this particular tree. So it's all just syntactic nodes. So you've got a question? An expression of what this looks like? Yeah. Yes, I kind of want to hide it. I'll just talk at you because there are no markers right here. But it's a bit of a mess. But it would look something like, so let's do 5 plus 3. 5 plus 3 would look like op node. Then we need the plus, so that's going to be for the sig here. So it's op of add, and then we need to do the expra. So it's op of add of var of 3 of var of 3. So it's a mess. And so what you want to do when you do this is you want to make smart constructors that build these things for you so that you don't have to go through the difficulty. And a direction I could have taken this talk in would be, rather than having you, so a direction we could go in is to use something called data types a la carte, which is a technique that allows you to sort of build larger syntax trees from smaller ones in a compositional way, so that with your smart constructors, you don't have to go through the headache of dealing with the fact that you have different effects playing around. So good libraries that use algebraic effects these days will provide you with some way of dealing with that particular problem, so you don't have to write stupid things like op of add of var of x of var of y. I mean, that's just crazy. Yeah, good question, thank you. Yeah, you've got a question.
With this instantiation of the free monad, the leaves have void values. So wouldn't the value at the expression tree of 5 plus 3 be op of add of op and then numf something?
Yes, thank you for the correction. You're absolutely right, yes. Okay, so what I was explaining to you in the example when you asked was actually a free of expra f of, and then I think I just lied outright. So it was probably free expra f of a free expra f of something. So yeah, thank you for the correction. So actually, what I should have said was it's app of addf of, sorry, op of addf of op of numf of 3 of op of numf of 4, right? That's what I should have said. Yeah. So indeed, you really don't want to do this, right? Okay. Okay, so that tells us a little bit about syntax trees, and now we need a way of managing these syntax trees and handling them down. And the analogy that I'd like to make about the way algebraic effects are compared to monads and transformers is that to some degree, it feels to me like working with monads and transformers, when you're defining how things work or how the monads should work, it's a little bit like writing recursive functions for lists. So you have a list, and you want to do something with the list, you write a recursive function that deals with it. Who controls how you use recursion? Well, nobody. You're up to you to do whatever you like with that, and you're free to have fun. Whereas very often what we do is we try to encourage people to use folds over lists. So folds do structural recursion over the list and ensure that your list is consumed completely before you can continue. And in the same way, if you're just working with an arbitrary monad, there's a sense in which you want to be defining your monad and how exactly it interacts with the operations. You're kind of free to do what you like, and that freedom can be dangerous. Whereas if you're doing things in the algebraic effects sense, then you have some constraints to how you do things. You have to work with algebras instead, which are basically the equivalent of working with folds that constrain the way you can move through the tree. So that's kind of at least an intuition that I hold for how these things work out. And it comes back down to denotational semantics and giving the meaning of syntax in terms of the meaning of its parts and then combining those parts. So the handle function is the thing that basically folds down the syntax tree, and it takes two parameters. It takes this thing called sig b to b, which is what we call an algebra, and it takes in an a to b function, which is called the generator. And the idea is that we're going to take a free sig of a's, and we're going to interpret this into some value b. So the leaves of this tree have type A. We need to make something of type B. Thankfully, we have this function called the generator that knows how to turn A's into B's. And so we can just apply that generator to X when we've hit a leaf. Which means that you can imagine we're starting off with a tree. It starts off with leaves of type A. And now we've kind of transformed all those leaves into values of type B. And so now we're going to work up the tree, transforming values as we go, transforming nodes so that the whole thing eventually will be a B. And that's what this second clause does. So this up part here says, I've got an operation. I don't know exactly what operation it is, but I do know that it came from a signature functor, which means it's a functor. And so I can take that operation. I can map handle alggen on this. Now, signature functors are functorial exactly in the parameter that says where the rest of the program is. So the parameter of the functor says, here is where the program continues. So this fmap handle alggen says, please go into the places where that program has continued and do some more handle alggen down there. So handle what's going on in the bottom part. So having done that, your operation nodes will now contain the payloads B rather than the rest of the program, because now that's all been handled away. And so you're ready to just apply this algebra, which takes your node whose values are now B's rather than programs, and then collapses that particular node down. And so this is how you kind of proceed through the tree, working away at your syntax, giving it a semantics. And the point of the free monad is that the free monad is a monad for any functor f. So for any syntax that you give it within reason, so let's say it's going to be sums of products, so things that you would normally think of as syntax, then you have a monad instance. And somebody's done some hard work to prove that it's a monad so that you don't have to. And then you don't have to ever again. In fact, there's no need to do all the proving of these monad laws as we did with monads and transformers. Even if you start making your own operations and your own interpretations of those things, the theory tells us that everything is guaranteed to just work. You don't have to worry about proving things anymore. So let's have a look at how we add with algebra. So here is the expression f that we had earlier on. And then what does the eval function look like? It's this thing with an algebra and some kind of environment. Now, the env, remember, is the thing that transforms the leaves of our tree into the domain that we're interpreting in. So in this world, we're going to turn it to doubles. And let's say that our leaves are strings. So they're going to be variables that contain, things like the variable x or the variable y or something like this. And so maybe the answer variable is always 42 and everything else is 0 in this tree. Okay, that's the way you might want to assign your environment. And otherwise, you've got some algebra that needs to work out how to deal with numbers and how to deal with addition. So if it's a number, then you just do x. And if it's an addition, you just add things together. And that's all you need to do. And now we've finished defining our evaluation function for addition. Great. So what if we want to add the division to our problem? So we have to add division to this field here. And then here on the left-hand side is what we had previously when we did things using straight-out recursion. And here on the right-hand side is what we can do in this framework. And actually, the meat of it is this algebra function, because this is just the environment. So this is what we really need to compare with. And all we're doing is we're saying, OK, if we've got just on either side, then we add them. Otherwise, it's nothing is the answer. So this is kind of catching all the cases that we have, and in some sense is a simpler piece of code. So maybe it's cleaner, but it's not really modular. I've kind of just hacked in an extra constructor for division, and I've hacked in an extra way of dealing with the semantics in terms of the maybe monad. This is not working. So maybe we want to just go and think about this modular division version. So earlier on, I was saying what we really want is some kind of class constraint that tells us, I said, don't use maybe. Use a class constraint that says you're working with monad fail instead. So, and here I was in this example going straight for the maybe. And maybe that's not a good idea. Maybe I want to be a bit more general, a bit more modular. I can do something like this. So this is the same code, except this time we're working with the monad fail constraint, and we want to. So this is the code that we had earlier on from the eval. This is the new things in terms of new way in terms of algebras, and the code looks basically the same, right? Except now we've got this one extra line up here. So why did we bother, right? This seems like a complete waste of time. We've just interpreted a tree. We're using a monad transformer. And maybe we bothered because now our code is interoperable with other people's work. So maybe it's now interoperable with transformers that other people might be working with. But frankly, it doesn't seem like it was worth it, right? We've got all this extra infrastructure. We've got these syntax trees playing around. and we haven't really gained anything at all. So that was a big problem. Well, the answer to that question is we can compose signatures. And I think one cautionary tale I'd say about algebraic effect handlers is they're slightly hyped up. They're not as good or amazing as you might think that they are, but they're not that bad either, right? And so just be a bit aware when people say, oh, the algebraic effects are fantastic. I think they are. I mean, I do a lot of work in them, but they're not a good straight-in replacement for monad transformers straight away. I think there are some trade-offs that we need to think about. But something we can do with these things is we can compose signatures. So we can have a coproduct of signatures on the left, signatures on the right, and then that basically says that in your syntax tree, you're either deciding that it's a syntax that belongs to one world or belongs to another world. So you can have multiple bits of syntax coming together. And the point is that algebra is also composed. So if you know how to handle signatures on the left and signatures on the right, then you can handle coproducts of these things. And our goal is to handle a signature like this one part at a time. So we're going to first handle numf, then we're going to handle addef, and then we're going to handle divef. So we're going to walk our way through the tree several times. First, we're going to pass through the tree and deal with all of the numbers. Then we pass through the tree and deal with all the additions. Then we pass through the tree again and deal with all the divisions. And that will kind of work for us. So how do we deal with numbers? So basically, the only line you need to think about is effectively this one, which says if you're interpreting a number and you want to make a tree that contains this, then you can just return that number. So that's kind of that's all you need to do. And what we're doing here is we're combining this algebra, which works just for numbers, with what we call a forwarding handler, which says for any effect that's on the right-hand side inside the signature that's not an addition, for stuff I don't recognize, I'm just going to recreate that operation as a syntax tree, as a node in the syntax tree all over again, so that I don't have to worry about that right now. So I'm just going to put it back into the tree and say, I don't know how to deal with that. So this is how we deal with numbers. And how you deal with addition is basically the same idea. You just have an algebra that works only with addition now and does that part. And how do you deal with division? Well, we could do this whole monad fail m constraint and then say that's what we're handling our tree into. And then we could write this code. And so now we've isolated the part where we have this particular constraint, okay? And so now you can chain handlers together and you can write something that says, I'm starting with a free tree of numf, addef, divef, and doubles, and then I'm going to go into some context, m that might fail with doubles, and I do it by chaining things together in this way. But aren't we back into the transformer world again? Somebody had to prove that this transformer was true. If we have to choose a particular m, then we've basically lost all of our advantages. What's the point, right? We're back into the whole transformers are the way to go world. Well, it's more nuanced than that. Handlers can also generate operations such as generating nodes in the tree that indicate that failure occurred. So they don't have to enact on the failure straight away. They can simply say, something went wrong, and somebody else is going to handle that failure. I don't know who it is, but they will. And so what we're going to do now is we're writing a different handle for division. So it takes in division and the rest of the signature, and it produces, the rest of the signature remains untouched. Division is gone, but now we've replaced division with some failures. What does this do? Well, the algebra tells us that if we have two programs, we execute X, we execute Y, get the results. We check the Y. If it's a 0, then we emit a new operation that says, I failed with the division by 0. Otherwise, we do the division and carry on. And it just works. So this thing will detect any division node, do the division for you, and carry on. What I just did in this particular slide is I worked with, let's have a look. So this is generating failures, and now somebody has to deal with those failures. So what we're going to do is, here's the handle fail that says, if you see failure nodes, then you can deal with those failure nodes and return maybe values at the leaves of the tree. And here's the alternative version that says, maybe you want to do an either thing instead. So you can give these two different handlers, which give you these different semantics for how failure might work, depending on what you want. And then you can just chain things together. So you need a way of dealing with trees that have no syntax in them, so it's just a value at the end. And what you have for this handle expert is you start with numbers, addition, division, and then void at the bottom of the effect stack. And then you want to create a maybe double. Well, what you do is you handle the numbers, handle the addition, handle the division so that it emits failures, then handle the failures, and then run the whole tree, and that will work. And then similarly, if you want to do something that gives you an either data type, then you handle the numbers, handle the add, handle the div, handle the fail differently, and then run the whole thing, and then this should work for you as well. And look, Ma, no monads or transformers. So we didn't have to talk about monad transformers. We didn't have to do the proof of monad transformers. We didn't have to rely on them in any way. And we get some kind of compositionality as if by magic. There's no proof burden required. This is done. Now, so it may seem as if, oh, how, algebraic effects are much better than monad transformers. There's all of this stuff that you don't need to do. Well, again, it's much more nuanced than this. There are some trade-offs. You can't express every monad or transformer using algebraic effects, so there are some limitations. And so there's this paper that compares monad transformers and modular algebraic effects and talks about the class of algebraic effects where this correspondence exists. You can dig in later if you want to. So yeah, division, failure, and void, what an uplifting title, right. So I'm gonna change pace in the talk now. So that was, to me, the kind of introductory part to compositionality, and now we're gonna start talking about some stuff that's a bit more heavy-handed. So let's talk about algebraic effects, and let's talk about theories. I want to see where theories come from and what's going on with this stuff, okay? Because there's a really deep and interesting history to where these ideas come from. And, yep. So the idea with algebraic theories is that we have some kind of world where we have a signature that expresses different kinds of operations that we're interested in. So for example, this sigma monoid here is the signature for monoids. So this is the world where we're able to talk about monoids in the way we do computations. It consists of operations like epsilon, which tells you that's the zero of the monoid, so where there's no computation, and O plus, where that tells you that you've got some binary operation. And they come equipped with indicators that tell you how many different parameters there are to these particular operations. And so what we have down here, this sigma star x thing, that's just very fancy writing for the free sigma tree with variables of type x. So this is saying, what this is saying is, if you have a variable of type x, then you have a way of embedding that into the free tree. Well, this is exactly what the var constructor was doing for us. And this thing over here says, if you have some operation with its arity, so that's something like plus and 2 inside your signature, and suppose you've got T1 through TR, which is the arity of the operation terms, which are tree things, then you can form an operation with those as its parameters, and that belongs to your tree as well. So this is just really fancy notation for the op constructor, okay? So there's nothing to be afraid of here. And when we have a term, so this is a term constructed by our free monoid world, well, you might want to have some variables in there that, that you can play with, so you have an environment, and so you have a context, and this corresponds to the generator that we had earlier on. So again, no surprises here. And then, well, this is the bit the mathematicians get very excited about. These are the equations that tell us that we have a monoid that we're dealing with. And because we're Haskellers, we completely ignore these in our modeling of free monads. And so, unfortunately, the free monad world in the Haskell implementation at the moment takes no account of equations. There's no making sure that these things are true. But is that really different to the way we do Haskell anyway? So we have type class constraints, and we often say, and the class is subject to the monad laws. Who checks those laws? Nobody. So it's, in some sense, it's no different in this world as well. And so, what I'm doing here is I'm just pointing out the correspondences between all these different parts of scary theory and the implementation that we have that comes straight out. And then the monoid's signature here becomes just an epsilon or a mul with the arities tagged in as extra data types or extra parameters to these things. And then to answer the question earlier on about how would we actually write these horrible things, you can have some smart constructors that look like this, and then you can write a particular term like this as just a simple expression like this in Haskell. So the thing all works out quite nicely. Another thing that mathematicians get really excited about are models for these sigma monoid or for free monads. And the idea of a model is basically an interpretation of the syntax such that everything is nice and compositional and works out. This is exactly what the handlers were. They were just interpreting the syntax. And so I'm going to sort of skip through this and say, all we're trying to do here is we're trying to come up with some kind of interpretation in some kind of carrier. So this is the final value that we have for our computation such that we have an interpretation that knows how to deal with each of the different operations. And this corresponds to the algebra that we fed to our handler earlier on. So the theory dictates that this is what we want to be doing. Thankfully, we're doing it in practice. Where did handle come from? So again, this is just a big theory slide. And all I want to say is, if you do a whole bunch of category theory, you'll recognize this as being a diagram between what we call F algebras. So this says that, or in this case, sigma algebras. So there's a way of dealing with sigma algebras where you're dealing with a free monad. This is call, or this is, in other words, the op constructor we had earlier on. And then there's a way of having algebras, which are exactly the algebras that we were feeding before. And then that induces a handle alggen function, and that's the implementation that we were dealing with when we handled our operations. So the theory dictates exactly that this thing should exist, and that makes me happy. So the next thing I want to just point out, I mean, again, I don't know why I put this slide up really. The thing I want to point out is all this theory boils down to interesting commuting diagrams, one of which eventually becomes this thing on the right-hand side. And this is exactly what we call the algebraicity property. So the algebraicity property says that this diagram commutes. And one way to read that is basically this rendition in Haskell. And this is kind of the line that we're probably interested in. So when people say, what is an algebraic operation? The answer is an algebraic operation op is such that this holds true. So if that operation has n parameters, and then you bind k, so you want to do that operation, follow it by some continuation, then that's the same as doing that operation to each of the parameters inside the operation. So that is a defining property of algebraicity. So yeah. Okay, we're kind of nearly through the theory section. So I just wanted to point out that all of this is well founded in something called the junctions, which tells you about uniqueness of the handle function. So we know that's well defined, but I'm just going to gloss over this for now. And in the interest of time, I think I'm going to just move on to, I think I do want to talk about this. So so when I said you can have nearly any syntactic functor sigma, there are some constraints in what you can do. So you want to be able to have a way of saying that these things have some arity. And basically that's what allows us to write things like Boolean termed constructors that allow you to go one way or another way. And I think I do want to skip this because the theory gets a little bit hairy and I'm running quickly out of time. So the other thing I want to talk about was state. This is encodable because get and put turn out to just be encodings that look like this. So what does get do? It basically takes some state and then it forwards it into the rest of the program. What does put do? Passes the state S to the rest of your program, whereas put takes in some S and produces something that goes into the rest of your program. So these all things work out quite nicely as well. And again, mathematicians get very excited about the fact that it seems like we've got a problem because the arities are all breaking, but what we have is like a family of operations, gets and puts, one for each state that we're dealing with. And so it turns out that that's all okay theoretically as well. Now, this one is where I want to start honing in back in again. So we've got models for non-determinism. So we've got this either or situation, a bit like we had with square rooting, where you want to say either you have something, you have multiple values that you might be able to choose from. So that means that we have some kind of signature non-determinism that has failure and that has an or command. And you have some way of choosing between either, let's say, true or false values. And that allows you to write some code that looks like this, that says, choose whether you're going left or right, and then carry on down. And this is, in some sense, modeling non-determinism. So the point is that generic operations aren't always appropriate, but they might be. You'll notice when you get good at this kind of thing that you might want something like what we call semi-lattice laws to hold on the OR operation. So you want the OR operation to say something about how non-determinism should work. So failure doesn't matter if you're failing on one side, the other side can succeed, and vice versa. If you're just ORing on the same thing twice, then you should preserve it. And then you've got this associativity law. And it turns out that there are obviously many different models of non-determinism. And what that means is there are many ways of interpreting how OR works. One example, and this is just an ordinary handler in Haskell, is you want to list all the non-deterministic choices. In other words, if you fail, you say it's empty. Otherwise, if it's x's or y's, then you put those x's and y's together, and then you remove any duplicates. Another thing you might want to do, rather than listing all the different non-deterministic choices, is you might want to just pick the first one. So if you fail, it's nothing. Otherwise, you have a look at what's inside the left-hand side. If that's nothing, then you have a look at, you return what's in the right-hand side. Otherwise, you return the first value. So this is a way of picking the first value in your non-deterministic choice. And so this is where we kind of hit the limits of what algebraic effects can do. And from now on, this is kind of a very advanced material. And so what I want to talk about is there's a kind of problem lurking with algebraic effects. And it's to do with this particular piece of code. So we have here a program P. A program P. And the idea is that we are going to be searching a space for different solutions. So we've got lots of different programs here that we're going to run. And we want to get some solutions from that search space, and then, let's say, carry on with some computation. How might we implement this searching? There are many different searching strategies. So one would be you search for the first thing. One would be that you search for all things. And these are just different implementation strategies that you could implement as handlers, perhaps. But maybe search is an operation. Maybe it's an operation that, given a tree, produces a tree of all the options that you found in this thing. And just like an ordinary operation, it too has equations associated to it. And we just need to check if it's indeed algebraic. So if you go through the proof and you say, if you go through the check, if you're searching for anything in this list and then you apply some other computation, then searching through this might, let's say, give you back all the results like this. And then if you apply square roots to this, you're going to apply the square roots to each of the different results to give you this tree here. And if your idea of searching works out, then you can do this the other way and commute the square roots into here, and everything seems to be fine. So when we're producing all the solutions, we're kind of happy. But it's not always algebraic. So if you use search once, which returns just one value instead of all of the values, and you go through the same procedure of trying to work out whether this thing is algebraic, you see that here you're trying to search for one result here, followed by square roots, which is the same as saying I found the 4, and then I do it square roots, and I get this or minus 2 or 2. And here with search once, if the square roots is bound inside here, then you'll produce this tree where all of the different solutions are being emitted. And then when you search once, you're only going to get the left node, which is this minus 2. But these trees are different. And the point is that this is not algebraic. So that tells us that search is not an algebraic operation. And so you can't use it in an ordinary algebraics and effects system. That's just not going to work. But there might be a fix for this. And the fix is to think about things that are scoped. So that's to say there's going to be a special way of dealing with certain nodes in the tree where bind behaves in a slightly special way. It targets the particular endpoint nodes where you want things to happen. And the kind of research goal is to make sure that however we handle these kinds of operations isn't totally arbitrary. There needs to be some structure to it. It needs to be denotational in the same sense that everything has been so far, folds and collapsing things. So what the theory ends up telling us is that we want to add one more construct to the free monad. So I'm going to call this the programming monad instead, where there's this enter command that says, enter a piece of code. So that means go into some scope and do some computation and come back out. So the enter takes in what we call a sig prime rather than a sig, which is a higher order signature. It says this is what the operation for a scoped thing looks like. And it has this scary signature. And what it amounts to doing is it's the same as this commented out line. It says there's a particular node form in your tree whose variables have type X, but it's existential. So nobody gets to know what's happening inside a scope. But you do have an escape hatch so that you can escape from that particular interpretation if and when you're ready to do so. And this turns out to be just enough machinery to make the scoped operations work in a very similar fashion to the algebraic ones. So the theory tells us that there's going to be this new tree, and it's all well-founded in the right ways. And a big research question was, what about the category theory? We've got all these different question marks. How on earth are we going to make it work? What's going to happen? And if you sort of go through the theory a lot, you eventually end up with this beautiful code that tells us exactly how to handle these things. And there's all this difficult theory that you have to work out to go through it, which I don't have any time to go through right now. But roughly speaking, we're at the point now where we understand how to implement these things, but we haven't done so. So already, this is an implementation that works, but it's nowhere near ready for consumption at this point. So that's my take on modular programming with effects. We've talked about monads, we talked about free constructions and algebraics, and then we got far too lost in the weeds. But thank you for your time.
All right. Thank you very much, Nick. Questions? Yes.
Hello.
Hi.
So the last part about scoped algebraic effects. A friend of mine recently did his bachelor thesis on call by value versus call by name evaluation of probabilistic lambda calculus.
Yep.
And I remember something very similar happens there.
Yep.
Basically, that you have different outcomes whether you do call by name or call by values, and
Yep.
one of the ways to fix it is to introduce the probabilities under a quantifier.
Mm-hmm.
So yeah, I just wanted to ask if you knew about that.
Yeah, there's a quite close connection between this work and modeling call by name and call by value. This isn't quite powerful enough in order to do that. For that, you need something close to what we call latent effects, which thread through the current monadic context through your tree. So that's even more complex than this. I'm not really satisfied with the state of the art theoretically at the moment, so I think there are probably ways to simplify it. But yeah, certainly that particular use case sounds very familiar, and I think it makes a lot of sense. Yep.
All right, thanks.
Hi. I was wondering about the semantics of your scoped effect, like scoped algebras.
Yes.
Because can you like briefly explain how the semantics differ compared to like fused effects and polysemy?
Yeah. Okay. So I think polysemy uses this weave operation, which is somewhat magical. It's basically a distributive law that says how you can push or pull effects out of this thing. I think the origins of weave comes back to the first paper I wrote on the subject on scoped operations. And so I think that question isn't fully settled from this perspective yet. So the connection between the distributive laws and what's going on here is going to be through, so the connection between, so how do I start? So there's monads, and then we've got quasi-categories, and we've got bialgebras, and bialgebras give rise to distributive laws, and then eventually I think we can start paving the way towards something like weave, but it's not settled at this point.
Okay, thank you.
Hi. So for the search operation, you said it's algebraic up to semi-lattice laws.
Right.
What
yes.
exactly does it mean?
Okay, so I think it was somewhere, I can't remember, was it here?
Maybe.
This one.
Yeah.
Okay, so this is the search list example. We're searching with the whole list as being the thing that we want to return, and so every value comes back, right? And if you look at if we look at the two different evaluations, so this one on the left is where you do the square roots on the outside, and this is where you do things on the inside. On the far right-hand side, over here, this tree has -2, 2, -3, 3. This tree also has -2, 2, 3, -3, 3, and even in that same order. So if there was a way of saying, so syntactically, these trees are not the same, but semantically, if you were to imagine these trees to always be interpreted in a model where the semi-lattice laws hold true, then the associativity of the operation should also always hold true, which means that these two trees are indistinguishable because they're the same up to rearrangements. Does that make sense?
Yeah. Thank you.
Speaking of free monads, there is a development by Oleg Giselyov called freer monads that allow you to even not derive any functor instance for your AST. So I'm wondering, what are your views on that? Is that a more superior thing to free monad in general?
I think it's just is it superior? It's just a different way of doing things. it means that you can just attach you don't have to do the deriving functor. It uses the coordinator construction to get there. There's more in the Freer library. There's more in the design space than the Freer library gives you. So the design space for algebraic effects and how to do them is actually quite huge. And lots of these different libraries are poking at different parts of this design space. So Oleg's idea is very good in that direction, but maybe the library isn't good in other directions. And so I think I wouldn't say that's the library to go for just for that particular feature, if that makes sense. Yep.
Are there any more questions? Yes, here.
Hello.
Hey.
So if I understood you, from your slides, the scoped effects kind of fix the non-determinism in the...
Yeah. So what the scoped effects do is they allow you to isolate where bind is allowed to intercept the rest of your code. And in particular, it says you can only intercept it after you've dealt with this scoped operation.
So are there any other examples different from non-determinism?
Yeah.
That can be of use?
Yeah, there are absolutely tons of examples.
Okay.
In fact, almost everywhere, in every MTL class, you always have the kind of the algebraic parts, and then you always have these ancillary functions, which would normally be dealt with by handlers. So for example, in exceptions, you always have the catch. Now, maybe you want to interpret catch in different ways. That's a scoped operation.
I see.
If you're looking at state, or let's say reader, and you have this local, which keeps track of the local state and then resumes to that state once you're done, that's also a scoped operation. And it turns out that almost every time you're trying to interpret something in a monadic context, you end up having a scoped operation that's just sitting around the corner. And another way to see this, or to say it, is almost every time when you have a handler over an ordinary algebraic operation or set of operations, you might be defining a scoped operation at that point. So it's not sufficient to work with just algebraic things if you want to take the perspective that what we're doing is giving denotational semantics to our syntax.
So could you, for example, have different interpretations for different catch scopes?
Yeah, so for instance, let's say you want to catch errors, and every time you catch an error, you want to report off to a web server that something went wrong. Or maybe you don't want to report to a web server, you want to save it to a file. Or maybe you don't want to report at all. Now you've got three different semantics. Are you in your testing framework, or are you running on production? Which semantics do you want to give? So having a fixed single definition of how catch works, I think, is too restrictive. Yeah. Maybe you want different things, in which case that's exactly what you want.
Cool, thank you.
Yeah.
So is the research for scope effects ready for real-world Haskell applications? Because there's this infamous bracket operation which everyone insists effect library must support. So is it possible to implement this way?
I think that's still research in progress. I'm not satisfied with where we're at just yet. I think that there are still some modularity issues that I want to iron out before we say we're ready for a library, which is why I'm holding back on actually releasing one. I think the ideas in the fused effects library are really, really good and very close to ideal, but I still think we're not there, but we're getting close.
Okay, thank you.
Yeah.
Okay. If there are no more questions, then please, another round of applause for Nick. Thank you very much for having you here.